Hi class, I wanted to make a short video about the relationship between analysis and design and how you can use this relationship to solve design problems. So think back to when you were learning arithmetic. You learned how to evaluate an expression like 1 plus 1, and it gave you some sort of result. You had to learn how to do this arithmetic before you learned algebra. In algebra, you started solving equations like -1 plus some unknown x is equal to 1. You need to figure out what x is. And so now, at this point, you know that they're really two sides of the same thing. In arithmetic, over here, you ask, what's the result of these two things that I know? I know 1 and I know 1. What is the result of that operation? In algebra, you ask, if I know this -1, what x do I need in order to make the result equal 1? So solving an equation is just the inverse process of evaluating an expression. You just have to work backwards. And this is precisely the relationship between analysis and design. At the beginning of assignment 3, for instance, you're given a bunch of parameters. You're given the motor power, I'll call it P, and you're given, say, the shaft diameter, I'll call it D. And you're asked to find out whether it's going to yield or not. And so basically you need to figure out what the maximum shear stress is in the material in order to determine whether it's going to yield. And the operations that you have to do are a little bit more complicated than just addition, but really there's a function that takes you from all of the things that you're given to the answer that you're looking for. The design process is just the inverse process of that. You need to go backwards. In design, you're still given the power, and you still have some relationship that takes you to get the maximum shear stress in the material, but you need to figure out what diameter the shaft needs to have in order to get you that shear stress. So I'm just going to circle the unknowns to make it a little bit more clear the relationship I'm driving at. The 1 and the 1 are known in arithmetic, and the result is the unknown thing. -1 is known, the 1 on the right-hand side is known. You're trying to figure out what value of x gets you there. Over here, you know the power in the analysis problem, you know the diameter in the analysis problem, and you're trying to figure out what is tau max in order to determine whether it's going to yield or not. And in the design problem, you still know the power and you know what tau max you're trying to get. You're trying to get it so that it's equal to the yield strength divided by 2 divided by the factor of safety. You know what that has to be. You're trying to figure out what diameter will get you there. So let's look at how to apply that understanding in Excel to solve both analysis and design problems. So we're going to start with an analysis problem. And this is how I typically set up my spreadsheet. I have a symbol column, and that's just the symbol I use to represent the quantity when I'm writing the equations by hand. It's helpful because now you can easily see, I've got D, P, omega. These are all the symbols that I would write by hand. It's helpful because now you can see and communicate the relationship between the calculations that you have in your Excel table and what you write on paper. The description specifies what quantity the symbol represents. So D is the shaft diameter. And then in Excel, everything needs to have numbers, so we've got values and units for everything. So at the top of my spreadsheet is everything that I already know, the things that I'm given about the problem. I call them inputs, right? I'm going to directly enter into the cells these quantities. You can see I've entered 0.25 right into the cell, 5, 1725, etc. All of these I entered in directly. These are the inputs, the things that I'm given. Now in the middle, I'm going to calculate some of the quantities that I'm not given directly, but they are really simple to evaluate from the inputs. So the radius, for instance, is just half the diameter. So you can see I've linked it to this cell above here, but divided by a factor of 2 because that's just a fact. The radius is half the diameter. I decided not to make a cell for this number 2. I entered it right into the equation because that's never going to change. The radius is always going to be half the diameter, and there's nothing to change about that. Likewise, the power here, well, that's just the power up here, and I've multiplied by 550 to convert to foot-pounds per second, and then multiplied by 12 to get that into inch-pounds per second. And 550 and 12 are never going to change. They're constants that I can just plug right in because it's a fact about the conversion between power and two different units. And then this tau allowable here, well, that's just the yield strength of the material divided by 2, because that's what Tresca's criterion says. And we've also divided by the design factor as well. And this is the maximum stress that you're allowed to develop in the shaft. So further below, I get to some outputs of the problem. These are things that I want to know that I can calculate from the inputs up here and the intermediate things. For instance, this motor torque here depends on both power and the motor speed. I calculate the tension in the belt here from the motor torque and the pulley radius. And I'm calculating the normal stress from the internal bending moment in the shaft and also the radius of the shaft. And finally, I do have a formula in here for the maximum shear stress in the material. It depends on the normal stress in the shaft that's due to the bending moment and the normal stress in the shaft due to the torque. And it's kind of a Mohr circle type calculation. I'm not going to show you what it is because that's part of the answer. So if I change an input up here, then all of the output cells are going to change appropriately because formulas for the outputs rely on the input cells. I wouldn't want to directly enter the input values into the output cell formulas. For instance, I'm not going to want to take the diameter, the shaft, and plug it directly into the equations for the normal stress in the shaft and the shear stress in the shaft, right? Because then if I were to change my shaft diameter, I'd have to change the number in both this formula and the next formula. So let's see how that works. I'm going to change one of the pulley, or both of the pulley radii, so I'll make it 3 and 7, let's say. And you can see that as I changed those, a bunch of the numbers down here changed. So this is the analysis problem. Given the inputs, find the outputs, and in particular, we're interested in what is the maximum shear stress in the shaft. So the design problem is just the inverse of the analysis problem. We're going to work backwards. We're going to say, given all these parameters, all of these ones, what shaft diameter do I need to make sure that the maximum shear stress down here is equal to the maximum allowable shear stress? I think that I can unhide this right now because I've changed some of the numbers so that you can see that, all right, I want this number to equal that number. What diameter do I need to make that happen? So it looks like I'm going to bump this up to 0.5. Let's see, I'm at 50,000. I need to get to 11,000. 0.75. All right, I'm getting closer and closer, and I could do this until I made this number equal that number. So you see how I've turned this analysis spreadsheet and I can use it to help me do the design. But because we brought our whole problem into the world of math, and computers are really good at math, there are algorithms that can do this process of changing the diameter such that this cell equals that cell for you. And in Excel, one way that you can do that is goal seek. So goal seek, you go to the data and what if analysis, click goal seek. And so what do we want to do here? It's prompting us, what cell do we want to set to a certain value? I want to set the maximum shear stress in the shaft to a value of, now unfortunately I can't just click on tau allowable, I'm going to have to type it in. I'll show you how to get around that. But I want to set it to 11,250 by changing cells. What cell am I allowed to change? The diameter of the shaft. We say OK. And it changes numbers for a while and ends up finding a solution. Now sometimes there might be a small amount of error in the solution, and that's okay. It can't always get the exact answer, but it gets pretty close. So we say OK. Great, I have found the shaft diameter that is required in order to make the maximum shear stress in my shaft equal the maximum that it's allowed to be, which is the yield strength divided by 2 and then divided by our factor of safety. Now all these numbers are different now from what you should have at the end of your solution because I've changed the pulley radii. Now again, when I did that in goal seek, I had to manually specify what this value is. I couldn't link to another cell in the spreadsheet, and that's unfortunate, but you can get around that. So the condition of equality, the cell that you want to set, equaling a value, when it equals that value, then the difference between them is 0. So I'm just going to make a cell that's the difference between the maximum shear stress in the shaft and the allowable stress. So I'm going to change this a little bit, mess things up, and I'm going to calculate the difference between the actual stress that I'm achieving and the allowable shear stress in the shaft. And I've called it the overload because it's the amount by which your shaft is overloaded, the additional stress beyond what it's supposed to be able to handle. And the idea now is we want to make it, we're going to change the diameter 0.75, 0.9, so it's positive now. If I make it 0.9, then the overload goes negative. So if the number is positive there, then the shaft has more load that it can handle. If it's negative, the shaft has less load that it can handle. And we want to find the sweet spot where it's exactly equal. The diameter is such that the maximum shear stress in the shaft is exactly equal to what the shaft can handle, what we're allowing it to be. So we go to goal seek, and we want to set the overload cell to a value of 0 now, and we're allowed to change the diameter. We say OK, and it solves, and it's going to find the same answer for us. And that way we can just link directly to a cell so we don't have to type in the value into the what if analysis every time. So that's why we spend all of this time learning how to analyze things. If you know how to analyze things, then in many cases it allows you to design them.